Synchronous motors. In this presentation, we're going to look at some animations that show how a synchronous motor functions with the different speeds of both the stator and the rotor. Let's get going. The first thing we need to know is that the synchronous motor has two very distinct circuits. One of them is the T terminals, which connect to the three-phase supply, and the other is the F terminals that connect to the DC coil. If we were to remove the rotor from this motor and energize the stator winding, what we would see is that a rotating magnetic field would be set up in the motor in exactly the same way that a skim motor would. Now this synchronous speed would be calculated by the number of poles in the motor as well as the frequency applied. If we were to instead energize the two field connections to a DC power supply, it would energize and force current to flow through the winding that's located inside the rotor. If we were to take the synchronous motor and to start it with full three-phase voltage, a couple of things will take place. First, we see that when we energize the stator, the rotor starts to move, and that's not because the coil is energized in the middle, the field coil. It is only because of the armature winding, which slowly brings the rotor up to speed. At this point, there's really nothing that separates this motor from a skim motor. The rotor is turning at a low percent slip around the 3 to 5% range. Now what we're going to do is energize the field coil with DC voltage. As soon as we do that, we notice that the speed of the rotor picks up. It immediately locks into the stator magnetic field and is now operating at 0% slip. The synchronous speed, it remains unaffected. It's still the number of poles and the frequency. The rotor speed is now exactly the same as the synchronous speed. If we were to take a look at this synchronous motor now with adjustments on the DC field side, we'll notice that some interesting ramifications take place. Right now, this synchronous motor is running under full load, as in we have brought it up to speed, we've synchronized it, and it's currently turning its rated mechanical load connected to the shaft. You'll notice that the volt DC source is set to approximately halfway or medium DC excitation, which is resulting in a low stator current. Remember, the stator current being the T1, 2, and 3. It's operating at a low stator current, and the power factor of the stator, or the three conductors coming in to supply the motor, is unity, so 1. It's a power factor of 1. If we were to lower the DC excitation, the value of current that flows to the field winding would lower as well. And if that current was lower, it would mean that there is less DC magnetic flux that is being introduced inside the motor as it spins. Now, the ramification of this is that we are now going to have an increase in current on the stator side. Now, the current value that's required from the source is increased, it's lagging. And so what that means is that although the motor RPM has been unaffected, the motor now requires more lagging VARs from the source. So this wouldn't really be advantageous, would it? We don't want to adjust a motor so that it is drawing more lagging VARs from the source. So let's go back to the original situation of medium. We're medium DC excitation, and we're at the lowest possible stator current. Again, unity. What would happen if we were to increase the DC excitation? So I'm adjusting the dial to increase it. Well, what that means is that with more voltage or DC voltage, I'm going to increase the current that is flowing to the field coil in the middle of the rotor. Now, if I increase that current, I'm going to increase the amount of DC flux that is being interacting with the stator magnetic flux that's rotating. The result of that is that, again, we're going to have high stator current, but this time, notice the difference. We now have a leading power factor. And what this means is that we are now, with the motor RPM still being unaffected, delivering leading VARs back to the source. We are power factor correcting. Now it's kind of hard to show direction of arrows and where these leading and lagging current values would be traveling to or from the source, but essentially what the synchronous motor is now acting as is a infinitely adjustable capacitor bank that can be regulated by a control system on the dial so that it is continuously adjusting the DC excitation to provide just the right amount of leading VARs to the facility.